got my Burlington Gold. That's what I care about.
Oh, that's good.
Yeah.
I'm about to get my night goals.
Yeah.
And zombies are. Oh, I meant in multiplayer. I got my
I don't play multiplayer.
It's fun. Just quick scoping dead.
I can't snipe for my life.
It's so fun.
I'm a pro.
Here we go.
You.
So we're gonna go over similar stuff to what we've been talking about. All right, we've been talking about kinetic. We've been talking about kinetic, and we've been talking about potential. All right, that's kind of what we went over on Monday in this class, right? We're gonna add one more thing to that. One more thing. All right. Yeah, elastic. How'd you know? That was genius.
I know.
Like, I feel like
I'm
you
just
already.
surprised that I can still read.
Yeah, I feel like you already know what we're talking about. All right.
Fans working on those.
Let's see. Do we want to do one more?
I mean, damn.
Let's do one more example. That's the first one. Like I said, we're going to skip around on your notes for a little bit. But we'll do this one. A player hits a baseball. What happened to all my papers? Well, it's just silly. Did I have more of those? There we go. Okay. Yeah. Wait, mine's different than yours?
No. What's the same? No, it's the same.
Okay. A player hits a baseball with a mass of 0.86 kilograms over the outfield fence. The ball leaves the bat with a 36 meters per second. And a fan in the bleacher catches it 7. Oh, don't look at the answer.
Too late.
Neglect air resistance. What is the speed of the ball when it is caught? Okay, so there's various things we have to take into effect here. So I'm gonna try to zoom in a little bit on my paper because I have the same thing you have. All right, I'm just gonna be using my little sheet here. Okay, so so we had a baseball player, and there's his bat. All right, and he hit a ball, and there's a little dude up here in the stance, and he caught it right there, right? And the information we know is that it left the bat at 36 meters per second, and we know that this guy caught it 7.2 meters above where it was hit. Okay, that's what we know. So if we have to take into effect the mechanical energy initial and is equal to the mechanical energy final. All right, so what I'm going to do is PE initial plus KE initial is equal to PE final plus KE final. Okay, so what's my equation for potential energy?
Mass
And
times
gravity.
height.
Yeah. All right, mass times gravity times height. All right, so potential energy. So my mass, 0.86. You guys see that all right? Am I writing big enough?
That's fine.
I can zoom in a little bit. 0.86. I just got to kind of write small to make this fit. Times gravity, 9.8, times my height. My potential energy height. Well, if this guy's 7.2 meters above, I don't really know my height, but I do know that this could be 0 and that could be 7.2. So 0 makes it a lot easier. This is kind of like my line 0, right? So my height, I'm going to say is 0. Okay. And then plus the kinetic energy, which is half the mass times half the mass. So half of 0.86 times the velocity squared. All right, so my velocity squared is 36. Does that part make sense? That's my initial. Okay. So my final, if I look at my final, okay, potential energy is mass times gravity times height. Now I know my height. If my original was 0, my height now is 7.2, right? Because that's given in the problem. So now I can do my height. Okay? And my kinetic energy is going to be half the mass times velocity squared. And that's what we're solving for. It said, what is the speed when it's caught? So v squared. All right, so we know all of this is 0. All right, I need to get a calculator out. Okay, I got 557 for this side. Got 60.9 right there. And for my final answer, I got 33.97 sig figs, 2 sig figs, 34. I got V to be 34 meters per second. All right, so hopefully you guys will see this in time and time again. The initials are going to equal the final. We're going to do that for many, many future problems. Well, a few future problems. Okay? Yes?
Are we going to do growth at any point? Or objects that aren't just rectangular or clear?
I'll have to see.
Or drag on rotating objects?
I'll have to see. Because, I don't know. We'll see how fast we get through this. Like this chapter. All right. Elastic potential energy. Okay. Now, this is where elastic comes into play. All right. So I'm going to show you. All right. The elastic potential energy, I would write this equation down right here. EPE is equal to 1/2 kx squared. Okay, so that's what the elastic potential energy is. Okay, where K is a spring constant. So that's a constant. And we already know X is displacement, right? X is displacement from future chapters, or past chapters. Okay. So that is what that analyzed, okay? And I would also write this down real quick. And this is known as Hooke's law. So, well, I guess you only need the equation part. The force of the spring is equal to Kx, which is the same, pretty similar to up there. But that's Hooke's law, and that's what tomorrow's lab's about. So I'm happy I got this far. All right? Yeah. All right. So if you look at this, we know mechanical energy is equal to mechanical energy, initial is equal to final. So this is what we originally had. We're just adding the potential energy, the elastic potential energy. Does that kind of make sense? Got those two equations down. So, like you see, or yeah, we'll do a few. Whoa. Okay. So if we look at an example of this, what this looks like. All right, example number 5 says, was everybody good writing that down? Okay. Example number 5 says, when a force of 120 newtons is applied to a spring, it causes it to stretch 0.0225 meters. What is the spring constant? So these, all you got to do is, well, the equation, let me see, get this right there, okay? The equation was force is equal to kx, the spring, that's Hooke's law, right? And I'm given force, my force tells me it's 120. My displacement, I know x. X tells me it's 0.0225. All you got to do is solve for the spring constant, which is k. So all you got to do is divide. Okay. And when you divide, my answer, I got to be 50, well, 2 sig figs. So it's 5,300.
It would be 54.
2 sig figs, 1, 2.
But it's 120.0. Yeah.
Ah.
Worse we did.
Ah. See what you did there. So technically it's 3 sig figs.
Technically, we do this since it's your problem.
So 5,330. And the unit for these are Newton meters, Newton per meter. All right, that's the spring. Oh, you can't see that. Newton. It does.
That's a pretty large number.
It is. Okay. Now, it says, what is the potential energy of this spring when it's compressed? So all we have to worry about is the elastic potential energy. Oh, my screen froze. Come on, come on. No. There we go. I'm gonna zoom out a little bit. I feel like I was in pretty tight. All right, so the elastic potential energy. All right, hopefully we wrote that equation down. That is 1/2 k x squared. Okay, well, I was given k, so I know k, and I'm given x squared right here. Well, I'm given x. So you just got to plug in your numbers. So 1/2 of 5,330 times 0.0350 squared. You plug it into your calculator. Anybody get an answer? What you got?
3.27.
3.27? Perfect. 3.27. Potential energy. Energy is in. Oh. That's force. Energy is joules. Energy is joules. So just big J. Energy is joules. Okay. How's that problem feel? Let's try one more. Yeah. Let's try one more. 1.7 block slides horizontal friction surface until it encounters a spring. Okay, so if you draw this out, what I like to think is there's a spring over here, and there's a box going that direction. Okay, and then the after, so this is the initial, and the final says it's going to be compressed. So there's my spring and there's my box. It's the best drawings I can do. Okay, so until it encounters a spring with a spring constant, so I know K is 955. When the block comes to rest, after compressing the spring a distance of 0.046. Okay, now I'm going to write out a lot of things, but I don't want you to write this out. Okay, so what you have is potential energy initial plus, like I said, I don't want you to write this out. Elastic potential energy initial is equal to potential energy final plus kinetic energy final plus elastic potential energy final. Potential energy is, what number is that going to be? All right, so potential energy is mass times gravity times height. And if it's on the ground, what's the height? 0. That's going to be 0, which means that's going to be 0. Okay, that wasn't too bad. Kinetic energy, is it moving initially? It is. Okay, so I'll keep that. Elastic potential energy, is a spring being compressed? I can get rid of that. Initially. Final. Am I going to have any kinetic energy in the final? No, it's going to be stuck. So literally, all you're going to have is the kinetic energy in the initial is equal to the elastic potential energy in the final. Does that kind of make sense? Like, there's a lot of factors to consider, but a lot of them are zeros, which makes our job pretty easy, right? So I have half the mass, 1.7 times velocity squared, which I don't know, velocity squared, is equal to the elastic potential energy is 1/2 times the spring constant. So the spring constant was 955 times it by x squared. So x was 0.046 squared. And oh, I can see that. And all you got to do is solve for v. Yeah, what you got?
There's an easier way to solve this. What you do is it gives you the distance that it compresses the spring.
Yep.
And the spring constant.
Yep.
And it says that it comes to a rest. So for it to come to the rest, the force in both directions has to be the same. So you can just multiply 0.046 times 955, and then divide it by 1.7.
That was a lot of words, but I really didn't understand.
Did that work? What's your answer?
25.84 meters per second. Wait.
You need to do the half.
No, the new way
Something.
I'm intrigued. My answer, I got 1.
Yeah.
I got 1. 1.1.
Yeah.
So that is potential energy. How do we feel on Hooke's law? Spring constant times x. The elastic potential energy is the spring constant times x, or 1/2 spring constant times x squared. And both of these, I'm pretty sure both of them are located on your formula sheet, which makes life super easy.
I like it. It's kind of straight. It's a little bit more straightforward.
Bro, you don't have to think. I mean, you have to think, but you don't have to think outside the boxes.
Whoa, that was pretty cool, honestly. Not the best. All right, so tomorrow we are going to do a Hooke's law experiment. We're going to have springs. We're going to have masses. All right, we're going to try it out. I've never done this experiment. I'm going to try it after school. Matthew, you do not make good paper airplanes. I'm going to make one in about, give me about 20 seconds.
They're good. I just started throwing them.
No, I think they're just bad.
Well, Mr. Bowers threw one.
As long as you do that.
Oh,
That works. You can't call this out. Your own students just told you how to teach your class.
I never had it.
This is my 22nd paper airplane. All right. Usually they're better. Can I try it?
Yeah, sure.
Heads up. Heads up.
Oh.
That was my 22nd plane.
You can't get much higher, man.
Did somebody forget their hat back there? All right. Have a fantastic day, guys. I gotta go teach some math.
In Spanish.
Math in Spanish.
Yeah.
That'd be fun.
No, but not.
Have a 360.
Those extra problems on elastic potential energy, are we gonna do them in class?
Probably not.
So I can go,
Yeah, if you want.
because clearly I'm not sure.
If you want me to
Miss
check
Caleb
it, we
Telford,
do.
please conduct a reception
I'll try and
check.
get a little
Caleb
bit
Telford.
earlier so you can check out
Yeah.
the class.
Perfect.
Thank you.
Yeah.